Good afternoon. Thank you for joining me for this video on this warm summer day. I am Mr. Ish. In this video, we're looking at infinite series, whether they're arithmetic, geometric, or neither, but we're looking at the predictive value of 5 tests. 3 of the tests you're already familiar with, the comparison test, the basic test, and that ratio test by the French mathematician D'Alembert's ratio test. We know those, but there are also 2 other tests I want to talk about, but you already know those. You know them informally by means of all the knowledge you already have with regards to precalculus and calculus. I want you to think of all of these always in terms of functions. You have something here, n equals 1 or 0. We're looking at this. We can have a certain rule over here. You know what the rule would be. It could be anything, but this rule is a function. Think of it as a function. If it's a function, you can graph it. If it's a function, you can always do its derivative, and if it's a function, you can evaluate it in terms of an integral. 2 of these additional tests from the 3 you already know are coming from what you see over here, and therefore by means of this knowledge you know those. I will just formalize it in this video. At a very basic example, let's look at this, and let this start what we're looking at in this video. We're looking at a series 1 over n. You know 1 over n is synonymous with the function 1 over x. The fact I have 1 to infinity, I'm looking at a domain from 1 to infinity. And because I have that, I can graph it out. You know it would look something like this, and it would go onwards from 1 comma 1 up to infinity. If you were to open this up in terms of a series, you have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 onwards. All the way you would hit 1 over infinity. Now let's start looking at it in terms of the graph. When you're looking at this in terms of the graph, where does your function approach? As limit n approaches infinity, and I could have put an n over here just for consistency's sake. F of n, limit approaches what? It approaches this horizontal asymptote y equals 0, and that would be your output. Based on a graph analysis, you would think that this rule over here, this series over here is convergent. You would think that based on the graph, because your function is approaching a value y equals 0, and sometimes it could be right and sometimes it can be wrong. So based on the graphic approach, we're seeing that we have convergence. But when you look at everything here with regards to the basic test, you know, you're always doing limit as n approaches infinity. You're evaluating this. Is it approaching 0 or not? When you look at all of this, you're eventually hitting 1 over infinity, and yes, you are approaching 0 because your series is progressively getting smaller and it is progressively becoming and approaching 0. So based on that, we see it. Based on the graphic approach, based on the basic approach, we see convergence, and the graphic approach can be one of your tests. How about the comparison test? Compare what you have, n equals 1, infinity, 1 over n, and compare it to a known standard, which would look like n equals 1, infinity, 1 over n to the power of p. Now think about it. You here have 1 over n to the power of 1. Here p is equal to 1. Generally, you know, if p is less than or equal to 1, you'll see divergence. And you know, if p here, the exponent is greater than 1, you would see convergence. And here, there's no point in doing a line-by-line comparison or item-by-item comparison, because you already failed this part right here. You already failed it, and you're seeing divergence come about. Therefore, based on the comparison test, we're seeing divergence, and it would overwrite what you see over here, and we would have a divergent series. Now, what about that ratio test? We can evaluate this based on the ratio test. Then we'll talk about the last new test. The first new test is the graphic approach. I showed you based on the graph it looks convergent, but based on the comparison test it overrides it and it's not convergent. But what about ratio test? In the ratio test, you're doing a n plus 1 or a n. You're doing limit as n approaches infinity. If this ratio over here is greater than 1, you know you're divergent. If it's equal to 1, it's inconclusive. If it's less than 1, it's convergent. But what would be our a n value over here? It would be 1 over n. What would be our a n plus 1 value? It would be 1 over n plus 1. Then you would run it through here. You'd have 1 over n plus 1 divided by 1 over n. You'd have n divided by n plus 1. And now you'd evaluate this with regards to the limit as n approaches infinity. You can do your horizontal asymptote determination style of work here. You're doing the highest order variable with regards to the exponent. You divide the numerator and the denominator by it. We end up seeing 1 over 1 plus 1 over n. As limit n approaches infinity, this zeroes out, we see 1. And this 1 tells us we're seeing here an instance, this right here is equal to 1, so we're inconclusive. And therefore the ratio test doesn't help us out. 2 of the tests, the graphic test and the basic test, leaned us towards convergence. The comparison test leans us towards divergence. And the ratio test leads us towards it being inconclusive, and that doesn't help us out too much. We now have to look at the integral test because that will help us out greatly. But before I jump to the integral test, look at this. What did we end up here with regards to the ratio n over n plus 1? What did we start with? 1 over n. We started with something which is easy to graph in terms of horizontal and vertical asymptote to something which looks like this, and I can graph it out for you and you'll see the stark difference between the two. When you graph n over n plus 1, which is a rational function, you can look at it as x over x plus 1. You have a vertical asymptote, x is equal to minus 1. You have a horizontal asymptote, which is right here, your limiting value of your function, y equals 1. When you graph it out, you see something like this, and you see something like this. Where does this show you as limit as n is approaching infinity? Where is your function approaching? It's approaching y equals 1. Hence the inconclusive aspect of this, and the discrepancy between this in terms of the graph with that. Here your function was approaching 0, here your function is approaching a horizontal asymptote y equals 1. It's inconclusive. Let's look at the integral test. The integral test basically says that if your integral is convergent in terms of its evaluation, your series is convergent. If your integral is divergent, then your series is divergent. Remember, we're talking nothing here about area below curves. We're just talking about the general pattern and the trend. If your integral is divergent, no finite value is being assessed, we're just looking at pattern, then your series is divergent. If your integral is convergent, your series is convergent. This is exactly what we're looking at, 1 over n dn, or you can say 1 over x dx, because the n and the x are synonymous here with regards to the variable which is being looked at. If you were to evaluate this, you know, by means of improper integral procedure, you end up seeing divergence. So at the end of the day, this series here is divergent, and you would have to leave it to that. The comparison test and the integral test push you towards this conclusion of divergence, and that would be our answer. But you see how the 5 tests have come into play. Now what we'll do is look at a series of other examples very quickly, and we'll run through them. Let's evaluate this series for convergence or divergence. When you look at it from 1 to infinity, you're really looking at a function. You can graph this function, and let's graph it. When you evaluate for a vertical asymptote, you know you're getting a 1 over 2 vertical asymptote. When you evaluate for horizontal asymptote, you're getting a y equals 0. You have a graph over here which would look like this coming down over here. Based on the graphic approach, this function going from a domain 1 up to infinity, we can do it doesn't matter the type of parentheses you're doing. Going 1 to infinity, your function is approaching this 0. So based on the graphic approach, we're leaning towards convergence. So we would be leaning towards that. But what exactly is a series? You'll have here 1 over 2 minus 1, which is a 1, plus 1 over 3, plus 1 over 5, plus 1 over 7, plus 1 over 9, all the way up to eventually 1 over infinity. That's your series. Let's look at this with regards to the basic test. Limit as n approaches infinity. Is your series approaching 0? It is. 1 over infinity is equal to 0, so it is. So based on that, we're seeing convergence. But what about the comparison test? When you compare this, you're looking at something which is n equals 1 up to infinity, 1 over 2n minus 1. You compare it to a known standard, which can very well be this. We can put over here 1 over n to the power of p, where p over here should be at least greater than 1. What exponent do we have over here? We really have an exponent of 1, so it doesn't really help us out. So the comparison test fails over here, and you can't say you're convergent, you can say you're divergent, because each of these items will be less than each of those items as you start putting the values in of n equals 1 up to infinity. The comparison test fails. How about the ratio test? We can try the ratio test. There's nothing wrong with doing that, but we don't have to graph that function which will develop. We can just analyze it with regards to the ratio test. The an value here is 1 over 2n minus 1, but the an plus 1 value here is 1 over 2n plus 1 minus 1. You see how your n plus 1 comes right over here. You open this up, you have 1 over 2n plus 2 minus 1. You'll have 1 over 2n plus 1. You're doing this divided by that. Remember, it's always an plus 1 divided by an. You'll have 1 over 2n plus 1 divided by 1 over 2n minus 1. What do you end up seeing? You end up seeing 2n minus 1 divided by 2n plus 1. And now evaluate this with regards to a limit. You can do this. You can just do the highest order in terms of the variable and divide everything with that. You'll do 2n minus 1 divided by n. You'll do 2n plus 1 divided by n. When you do that, you'll have over here minus 1 over n, and you'll have plus 1 over n. These zero out as limit n approaches infinity, so you end up seeing 1. When this limit over here in terms of the ratio is equal to 1, it's inconclusive. So we're no longer working with that, and it's not convergent. So it could be divergent. There's one more test that remains to be utilized. It's the integral test. If you were to do the improper integral evaluation of this and it were divergent, then your series would indeed be divergent. We're not going to run it through the integral, but I'm going to set it up for you. It would be 2x minus 1, or you can do 2n minus 1 and then dx. If you run this through, you calculate it out, you will have a divergence. So you would have to say that this series is divergent. It's divergent because the comparison test fails, the ratio test is inconclusive, and the integral test leads you to conclusion of divergence. Only the basic test and the graphing test, or the graphing of the rational original function, were leaning you towards it being convergence. But remember, the basic test convergence is never 100% guaranteed. It can give you a convergent value, but in reality you can have a divergent outcome. So the value in terms of this with regards to convergence or divergence is this. It's a divergent series. Now let's look at this 1 over n plus 1 whole square. It's a good series. It's a function. How would you look at it in terms of its values? You start putting in 1 over here. You'll have 1 over 4. And then you'll have here 1 over, you'll put 2 over here, 9. Then you'll have 1 over, you'll put 3 over here, you'll have 16. And now you're getting the idea that it's like this: 1 over 36, 1 over 49, all the way up to 1 over infinity. If you were to graph this out and just look at the graphic analysis, you have a vertical asymptote here, x equals minus 1, and your graph would look something like this. That's what it would look like. Based on the graph, it's approaching here a horizontal asymptote, y equals 0. Your function here is approaching that. So based on the graph, you can say we have convergence at play. And we could be right with regards to that. But we're only looking at it from a domain 1 up to infinity. And therefore you look at it from right over here, you're looking onwards, it's approaching 0, so we see convergence. Based on the basic test, limit as n approaches infinity, this entire, let's just call it function, does it approach 0? It sure does. So it could be convergent. Let's look at the comparison test. You would compare this to a known standard which is known to be convergent. You have 1 over n plus 1 whole square, and compare it to this infinity n equals 1, something which looks like 1 over n to the power of p, where p here is equal to 2. Remember, p is greater than 1, then you know it's divergent. Here we're looking at 1 over n to the power of p, where p is equal to 2. Here we have something exactly like this. This looks almost like that, and therefore you can rely on this. If this is convergent, then this right here will be convergent. Think about it, each of the denominator is being increased, so each of these values will be mathematically smaller than each of these, so the convergence by means of the comparison test succeeds, and it clues you in towards convergence. We have the graph telling us convergence, the basic test telling us convergence, and the comparison test telling us it's convergent. Let's look at the remaining two tests, the ratio test, and we will look at the integral test. Based on the ratio test, we have an a(n) value which is always 1 over n plus 1 whole square. Based on the n plus 1 term, we have a 1 over n plus 1 whole square. We're adding an n plus 1 over here. This is just 1 over n plus 1 whole square. This right here is 1 over n plus 2 whole square. You would do this divided by that. So you do 1 over n plus 2 whole square divided by 1 over n plus 1 whole square. And you would evaluate this with regards to limit as n approaches infinity. And you would flip things around, n plus 1 whole square divided by n plus 2 whole square. And you can open it up. You'll have n square plus 2n plus 1 divided by n square plus 4n plus 4. Limit as n approaches infinity. What do you end up seeing? You'll end up dividing everything here by n squared, the highest variable with regards to its exponent, and you divide the numerator and the denominator. When you divide the numerator and the denominator, you end up seeing 1 plus 2 over n plus 1 over n squared in the numerator. In the denominator, you see 1 plus 4 over n plus 4 over n squared. Limit as n approaches infinity, these zero out. You end up seeing a value of 1, which is inconclusive. So the ratio test is inconclusive, it doesn't help you out. But we're still leaning towards convergence based on the previous 3 test results. So this is inconclusive, but it's not a big deal. The last bit of information you can obtain is from here. 1 to infinity, 1 over x plus 1 whole square. I'm just replacing the n's with the x. Anyhow, if you were to integrate this, you'd end up seeing convergence, and your series here would entirely be convergent, and that would be your answer. This represents the last question we look at in this video. From n equals 1 to infinity, n square plus 1 divided by n plus 1 whole square. What are the potential values here? If n is equal to 1, you're seeing here a 2 over 4. If n is equal to 2, you're seeing here a 5 over 9. If n is equal to 3, you're seeing a 10 over 16. If n is equal to 4, you're seeing a 17 over 25, and on and on. So it's a rather tricky series, but let's look at it in terms of a graph. If you were to graph it out, you can easily determine a vertical asymptote here. X is equal to -1. The horizontal asymptote is y equals 1. But literally our graph is going to be from 1 onwards. But if you were to graph it, you would have something which would look like that, and it would come like this and then it would go up. It would always try to get close to this y equals 1 horizontal asymptote right over here. It approaches a value here of 1, limit as n approaches infinity. Based on that, we're seeing divergence because it's not approaching 0. According to the basic test, limit as n approaches infinity. If you didn't have the benefit of this graph, how would you do this? You're looking at this, it's a complex function. You can't just look at it and analyze it. You can if you think about derivatives. If you were to put infinity here in place of this, you're just doing a basic limit evaluation. You'd see an indeterminate limit form of infinity over infinity come about. You can do the derivative of the numerator expression. You can do a derivative of the denominator. And you'll have 2n, and here you will have, by means of the chain rule, you'll have 2n plus 1, which would be 2n divided by 2n plus 2. And then you'd evaluate it with regards to the infinity. You still have this infinity over infinity form, so you do another round of derivative, the L'Hopital's rule. As you remember, you end up seeing 2 over 2, which is 1. Limit as n approaches infinity based on the basic rule. This is what we see. It does not approach 0, it approaches 1. Therefore, we're seeing a divergence here just like that. The basic test and the graph test have leaned us towards divergence. Now let's look at it with regards to the comparison test. According to the comparison test, you want to compare this to something which would look similar with a known standard. Would it look something like this, where p is equal to 2? We're using 2 because we have 2 over here. N equals 1 and infinity. Does it look like that? It's hard to judge. You have n squared plus 1 and this n plus 1 whole square. You can do a bunch of terms. We already have terms over here, but we can do some terms from right here. The first term would be 1 over 1. The second term would be 1 over 4. The next term would be 1 over 9. The next term would be 1 over 16. In the first item of this series, it's smaller than that, so we check out. But the second is not smaller than this. The third is not smaller than this. The fourth is not smaller than that. So the comparison test fails with regards to convergence. We see divergence over here. Even if you put like an n over here to justify that, you would not be 100% sure that this indeed is then a known standard of convergence, because you'd end up seeing n divided by n to the power of p, which you could say is n to the power of 1 minus p. You would lose that known standard, and you may no longer be comparing a test with something which is truly convergent. So stick with this, what you have over here with regards to 1 over n to the power of p, and utilize that as your standard. And based on that standard, it's divergent. What remains is the ratio test and then the integral test. When you look at this with regards to that ratio test, you know you're looking at something as an plus 1 divided by an with regards to a specific ratio. When you're looking at this, you have an an term, which is exactly what you see, n squared plus 1 divided by n plus 1 whole square. Your an plus 1 term is going to be the n plus 1 coming here in places of n. You'll have n plus 1 whole square plus 1 divided by n plus 1 whole square. You can simplify that. You'll end up having here n squared plus 2n plus 2 right here in the numerator, the an plus 1 term. Here you're going to end up seeing n plus 1 plus 1, which is n plus 2 whole square. That's going to be n squared plus 4n plus 4. You know you're going to take this term and you'll divide it with that, and let's see what happens. You'll have n squared plus 2n plus 2 divided by n squared plus 4n plus 4 all over n squared plus 1 divided by, open this up, you'll have an n squared plus 2n plus 1. You can flip this denominator around. You'll have n squared plus 2n plus 2 divided by n squared plus 4n plus 4 times n squared plus 2n plus 1 divided by n squared plus 1. Now, there's nothing wrong with us doing a little bit of a cheat. In the grand scheme, all of this is kind of meaningless. You can cancel with that. You end up seeing just n squared plus 2n plus 2 divided by n squared plus 1. When you apply the limit and you divide everything by the highest order degree of variable exponent n squared, you end up seeing 1 plus 2 over n plus 2 over n squared in the numerator. Here you'll end up seeing 1 plus 1 over n squared. Limit as n approaches infinity, these zero out, you end up seeing 1. With regards to this, again, everything here equaling 1, it's inconclusive, and you know that is not a very good thing with regards to the ratio test, but it's fine. It's inconclusive. We already know based on the previous tests that we're getting, and we're playing with divergence all along. This inconclusive is not a big deal. Remember, the ratio being larger than 1, divergent, ratio being less than 1, convergent, ratio equaling 1, inconclusive. What ends up happening with the ratio test when you have these rational functions come in and you start doing these limiting value of this function determination or this limiting value of the ratio determination, you almost always end up getting an inconclusive result. That's just the way it is. But that's fine. It's not a big deal. Let's look at here with regards to the integral test. In this video, for all the examples I've given you, I've kind of cheated my way here with regards to these improper integrals, because you know you'd have to spend time evaluating them. But if I spend time doing all of this evaluation, it would be such a long video. We can always do these integrals on the side. These n's could have been x's. When you evaluate all of this and you do it properly, you end up seeing a divergence over here. So in all instances, this series here is divergent. Remember, if the integral is divergent, the series is divergent, and likewise with regards to convergence. Remember, we're not evaluating the area below the curve here and coming up with a finite or an infinite value which represents the sum of that. We're not doing that. We're just looking at only the convergence and divergence. If this were convergent, the finite value here of the area of the curve would not be the same as the sum of that convergent series. But certainly a divergence here of infinity will indicate a sum over here to be infinity as well. But nothing more and beyond that. Remember, again, in all instances what we've looked at, the basic test, the graphing function test, you can call it that, the ratio test, comparison test, and the integral test. But we've cheated our way through the integral test by just running directly down to the answer without showing you the integral procedures. And these were all improper integral procedures from 1 through infinity. And generally for the integral test, you are looking at these instances from 1 to infinity, f of x dx. If it's convergent, your series is convergent. If it's divergent, your series is divergent. Think back to the very first one we looked at, 1 over x dx. That's exactly what we had. I'll very quickly run through this because it's quick and it's easy and it won't take too much time. You know, you would integrate this. You'd have natural log x. You'd look at everything here from infinity to 1. When you do that, you're doing natural log of infinity minus natural log of 1. This is 0, but this right here is infinity, so you end up seeing divergent. That very first example was divergent. The integral test shows us divergent, so we're good with that. When we looked at this one right over here, n equals 1 to infinity, 1 over 2n minus 1. The integral would be from 1 up to infinity, 1 over 2x minus 1 dx. Let's integrate this very quickly. If u is equal to 2x minus 1, du is equal to 2 dx, dx is equal to du over 2, u1 and u2. u1 is equal to 2 times 1, which is a 2 minus 1 is equal to 1. u2 is a 2 times infinity minus that, is still an infinity. We're looking here at from 1 up to infinity. What do we end up seeing over here? We have a du over 2, which is a 1 over 2. We have a 1 over u du. We end up seeing 1 over 2 ln u. And we're looking at everything here from infinity to 1. Do not resubstitute back because we're looking at a definite integral. We're seeing 1 over 2 ln infinity minus ln 1. In all instances, this is 0, but we're seeing an infinity over 2, which is still an infinity. So it's divergent. And that series which looked like this was divergent. Its integral test gives us divergent, and that's exactly what it is. It was a divergent series. But remember, the 5 tests, the predictive value is exactly what you would be thinking of in your head. In some cases they're very predictive, in some cases they're not. The basic test with regards to divergent outcome is always predictive. Other tests not so much so, especially with regards to the graphing test, but the integral test is quite sure. The comparison test is quite sure in terms of its predictive value. The ratio test can be good with regards to divergence and convergence, but you have a lot of cases of inconclusive coming out, especially when the ratio involves rational functions. That limiting value procedure ends up giving us a value equal to 1 quite a bit, which you know to be inconclusive. Before I bid you all a true farewell, let's look at this one we saw in our video not too long ago. I believe it was example number 3. Let's not shortcut through this one in terms of the integral procedure, because this will be convergent and the integration will show that to be the case. In terms of the series convergence, we're looking at from 1 to infinity. We have 1 over n plus 1 whole square dn. You would do u substitution or polynomial substitution. If u is equal to n plus 1, du is equal to dn. u1 and u2 new limits. With regards to this right here, u1 is going to be 2, u2 will still be infinity. your entire everything becomes here from 2 up to infinity. You'll have 1 over u squared du, which you can bring up by means of the laws of exponents. That's exactly what you have. Then it's a polynomial integral here. N plus 1 divided by n plus 1, you'll have u to the minus 1 divided by minus 1. You'll have everything here from infinity up to 2. When you look at this, you're seeing a minus 1 sit outside, but you're seeing a 1 over u in terms of this, which is equal to that, infinity and 2. When you do the final procedure over here, look what will play out. You'll have 1 over infinity minus 1 over 2. This zeroes out, but this with that gives you a positive 1 over 2. We're not focusing on the positive 1 over 2 because that represents the area of the curve, but this positive 1 over 2, the finite value, represents convergence for this specific series. But don't focus on the value here because that's area below the curve. It's not the sum of your series. It right here represents the convergence of your series, and that's it. Thank you for watching. Have a good day.